My doormat's looking a bit old. Yep, it's definitely worn out its welcome. Speaking of which, hello and welcome. In this video, we're going to add another tool to our integration tool belt, Trigonometric Substitution. Trigonometric substitution is a technique that will help us evaluate integrals involving expressions like the square root of a squared plus x squared, the square root of a squared minus x squared, and the square root of x squared minus a squared, where here a is some kind of constant. So it's not always going to work with these particular expressions, but a lot of the times when you see an expression that's like that, or some kind of other form like that, then trigonometric substitution can help out. The best way to learn about it is just to jump in with example 1. So here we have the integral of x squared dx over the square root of 9 minus x squared. Just a little aside, remember that if you have the dx up on the top of the fraction, that just means the same thing as the integral of x squared over the square root of 9 minus x squared, and then with the dx on the side. It's the same thing. It's just that sometimes people like to put the dx up on the top of a fraction. Now the first thing we're going to do here is, when we think about substitution, we think about taking a part of the integral and letting u equal that part. But with trigonometric substitution, it works kind of in reverse. We're going to take x and replace it with a more complicated expression. Now this is going to feel like it's going to complicate things, but it's actually going to make things easier in the end. So let's take our first step. What we're going to do is we're going to let x equal 3 sine theta. 3 sine theta. Now we'll explain in a moment why that's a good substitution to make. But we're going to replace all the x's in this integral with 3 sine theta. Now the dx would then get replaced with 3 cosine theta, d theta. So we're entering this new variable theta. We're going from x into theta. So we're going to replace all the x's with 3 sine theta. We're going to replace the dx with 3 cosine theta. And the integral that we're going to get is going to be all in terms of theta. So we'll have 3 sine theta squared over the square root of 9 minus quantity 3 sine theta squared. And then we'll have times dx, which gets replaced with 3 cosine theta d theta. So everything now is in terms of theta. Now again, this seems more complicated, but in a moment we're going to use our trig identities to help simplify this down, and we'll see why x equals 3 sine theta was such a good choice. So off to the side, what we're going to do is focus on that radical, the radical 9 minus quantity 3 sine theta squared. We're going to focus on trying to simplify that part. And maybe I'll do this in a different color. I'll go with orange. Alright, so we have the square root of 9 minus, I'm going to go ahead and square this 3 sine theta squared to get 9 sine squared theta. And if we work on this a little bit, there's a 9 that we can factor out. So we have the square root of 9 times quantity 1 minus sine squared theta. And if you recognize the 1 minus sine squared theta is we can replace with cosine squared theta. If you remember the work that we did in 7.2, kind of going the opposite direction, replacing a cosine squared with a 1 minus sine squared, for example. Here we're taking a step of simplification. We're using that Pythagorean identity to try to simplify the 1 minus sine squared theta. Because sine squared theta plus cosine squared theta equals 1, and you can solve for one in terms of the other. So this is great because we just took these two terms inside the radical and simplified them down into just a single term. We just have 9 cosine squared theta. So now we can apply the square root to both the 9 and the cosine squared theta. The square root of 9 is 3. The square root of cosine squared theta, technically speaking, is the absolute value of cosine theta. And let me just write off to the side here. If you take a number like x squared and you square root it, that's technically the absolute value of x. Because imagine if you were to plug in like a -3 into the left hand side, then you'll get square root of 9, which is +3. So you plugged in an x value of -3 and you got out an x value of +3. That's like taking the absolute value of that x value, right? So technically, if you're going to take a number, square it, and then take the square root of it, you're doing the same thing as the absolute value of that number. Okay, that's just a little aside. But what we're going to do is we're going to go back up here where we made our substitution, x equals 3 sine theta, and we're going to make a little restriction on the possible values of theta. We're going to say that theta is between -pi/2 and pi/2. What this is going to do is force sine, the sign that we're substituting for x, to be 1:1. This will force sine to be 1:1. Remember, if you have a 1:1 function, you can take its inverse, and later on down the road we're going to be needing to do that. So that's going to be useful not only for down the road when we have to get the inverse of our trig function, but also at this point, because if theta is between -pi/2 and pi/2, cosine is positive on that entire interval. If you think about -pi/2 to pi/2 on the unit circle, that's where the x values of the unit circle are positive. And so that's where cosine, which is the x value on the unit circle, is positive as well. So if you're thinking -pi/2 to pi/2, the x values are positive, so cosine is positive. And that means that we can drop these absolute value bars. If theta is between -pi/2 and pi/2, then cosine is positive, so absolute value of cosine theta is the same thing as cosine theta. Let me make that little note right here. We can take this step because theta is between -pi/2 and pi/2. Okay, well that simplifies a lot inside the radical, or simplifies the radical, it collapses it down completely. And what we have here is 9 sine squared theta, coming back to the integral, 9 sine squared theta on top. We've got 3 cosine theta on the bottom, based on all the work that we just did. And then we have another 3 cosine theta that's coming from the dx. And that's going to simplify even more. We have a 3 cosine theta canceling with a 3 cosine theta. So we just get the integral of 9 sine squared theta, d theta. Okay, and we know how to integrate trig functions, because in 7.2 that's all we did is integrate trig functions. We integrated things that have powers of sine, powers of cosine. So here we have a sine to the even power, which means we're going to need to use the power lowering formula to break this sine down into single powers of cosine. All right, so we're going to do that. Let me go ahead and bring the 9 out of the integral. So we have 9 times the integral of, now remember, sine squared theta by the power lowering formula is 1 minus cosine 2 theta over 2. Then we have our d theta. The half on the bottom, so the 2 on the bottom, we can pull out as a half. And let's go ahead and just integrate what we have on the top there. So we have 1 minus cosine 2 theta. If we integrate that, the integral of 1 will be what here? If you said theta, that's correct. Remember we're using, excuse me, we're, I just ate. So we're integrating with respect to theta. And so we have the integral of 1 is theta. Now when we integrate cosine 2 theta, we're going to get a sine 2 theta. But what are we going to have out in front of that sine 2 theta? That's right, it's going to be a half. And we're going to put our little plus c. Okay, so we're done integrating. The only thing is we're not quite back to the variable that we started with, which was x. So let's try to work back to getting the variable in terms of x. Now, one thing is we know everything that we can know about the angle theta, because of this relationship between x and theta that we set up. We know that sine theta would be x over 3. If we divide the 3 over, we get sine theta equals x over 3. That's going to allow us to draw a little triangle and get everything we need to know about the angle theta. But the problem is here, we have sine 2 theta. So if we're trying to go backwards from theta into x, it's hard to know what to do here because we're trying to undo an angle at 2 theta instead of just theta. So what we're going to do is we're going to bring the 2 theta down to thetas by using a double angle formula for sine. So you might remember that, let me write this out actually on the side. So you might remember that sine 2 theta, the double angle formula is 2 sine theta cosine theta. So this is a good one to remember. It goes from an angle of 2 theta down to an angle of theta, at least when you're dealing with sine. Now here we have 1/2 sine 2 theta, so 1/2 sine 2 theta is going to be, well, 1/2 times the 2 right there, which cancel each other out. So you just get sine theta cosine theta. All right, let's make those replacements. So we have 9/2 times the quantity theta minus sine theta cosine theta plus c. All right. Now, as a next step, I'll change colors. So as a next step, what we know is the relationship that we set up between sine and x. Sorry, between theta and x. So x is equal to 3 sine theta. So as we were talking about just a moment ago, we can solve this for sine theta. We get sine theta equals x over 3. And so we'll know everything we want to know about the angle theta, all the trig functions at angle theta, by setting up a little triangle. So here we're going to put the angle theta in this right triangle. And we know that opposite over hypotenuse for that angle is going to be x over 3. So the side opposite to theta is x, and the hypotenuse is 3. And with the Pythagorean theorem, you can get the third side. It's the square root of 9 minus x squared. Okay, so now we can get any trig function at angle theta that we want. We don't have to worry about trying to find a triangle that has 2 theta in it anymore because we lowered the 2 theta down to thetas. And so we've got this triangle right here, so we can get sine theta, which is x over 3, which we kind of already knew. But then we have cosine theta is going to be adjacent over hypotenuse on this right triangle, which is the square root of 9 minus x squared over 3. So that's great. There's just one thing left, which is theta. But theta is not too bad. You can take the relationship sine theta equals x over 3 and solve it for theta. And you get theta equals inverse sine of x over 3. Okay. So that is all we need then. So we have 9/2 times the quantity, inverse sine of x over 3, minus sine theta, which we said was x over 3, and then cosine theta, which we said was the radical 9 minus x squared over 3. And then we have our plus c at the end. So the only last thing to do maybe would be to simplify. So here we can distribute the 9/2, and we've got 9/2 sine, inverse sine x over 3. And then we have a 3 times 3 on the bottom here, which is 9, but then the 9 on the top of the 9/2 cancels, so we end up with just a half. So we'll have x square root of 9 minus x squared on the top, and a 2 on the bottom from the half. Okay, so that's example 1. Now how do you know which trig substitution to make? Well, here's a little table that can help you out. If you see a radical, like the square root of a squared plus x squared, then you'll want to make a substitution x equals a tangent theta. That substitution will collapse this radical down, and we'll write that up in just a moment. If you have the square root of a squared minus x squared, like we saw in example 1, we had the square root of 9 minus x squared, then letting x equal a sine theta is a good choice for a substitution because that's going to collapse that radical down to something simpler. And then if you have the square root of x squared minus a squared, letting x equal a secant theta will collapse that radical down. Also, you'll want to have your restrictions of theta. So for our example 1, we restricted theta from negative pi over 2 to pi over 2. That allowed us to find the inverse sign down the road, because sine only has an inverse if you restrict your values of theta. And similarly, for tangent, it's going to be the same kind of interval. We won't be including the endpoints because tangent is undefined there. And then for secant, it has its own pair of intervals, which are theta going from 0 to pi over 2, or theta going from pi to 3 pi over 2. Now, some helpful mnemonics for remembering which one goes with which kind of radical. The only one of these that has a plus inside of the radical is the one that you make a substitution for tangent. And so sometimes people will see that plus and imagine that it looks kind of like a t, and that reminds you of the t in tangent. So hopefully that mnemonic helps you. Now, how to distinguish between the sine and the secant substitutions, or the a squared minus x squared and the x squared minus a squared substitutions. Remember, a is a constant, so constant minus variable, or variable minus constant is what you have to distinguish between. Well, one way you can remember it, and this is a very crazy mnemonic. I was really racking my brain over this one. So you could say that it's a sin to ax your professor. Ah! So if you remember the ax is like a squared minus x squared, then it's a sin to ax your professor. All right. So hopefully those mnemonics help you out just a little bit. I wanted to show you again the collapsing of the radical in example 1. So here we let x equal 3 sine theta, and we kind of said we didn't explain why exactly. But you can see why that's really helping out here. When you replace the x with 3 sine theta, inside that radical, when we do our work over to the right, it collapses down because it sets us up for the form 1 minus sine squared, which we know is going to be cosine squared. Sets us up for one of the Pythagorean identities. And in order to get that set up, though, we need to make sure that the coefficients are matching. So whatever the coefficient is of the constant term, we have to have let x equal the square root of that, so that when we turn back around and square that x, we get back to that constant term. So we have a 9 that we have to match, so we let x equal 3 sine theta, so that when we square that, we get a 9 sine squared theta. That way we can factor the 9 out. And then we get 1 minus sine squared, which turns into cosine squared, and everything inside the radical collapses. Suddenly we don't have the radical anymore, which is great. So it's a similar kind of thing happening for these other ones. I just want to give you one little example of that. So right here for the tangent, you can see it collapsing. If we replace, so if we have the expression the square root of a squared plus x squared, and we replace the x with a tangent theta, then this will turn into a squared plus a tangent theta quantity squared, which is the square root of a squared plus a squared tangent squared theta. And here the a squareds are matching, so we can factor out the a squared. And we're left with 1 plus tangent squared theta, which we know to be secant squared theta. So at the end, we just get a and then secant theta. And we can drop those absolute value bars if we have the restriction of theta going from negative pi over 2 to pi over 2. Remember that on that the first and the second quadrants, the first and the fourth quadrants, which is where that interval is, cosine is positive, and therefore secant is positive, because secant is just the reciprocal of cosine. Okay, so there's an example of why the substitution a tangent theta works for the square root of a squared plus x squared. So it works similarly, like we saw example 1 for the sine theta, and it works similarly for the secant theta as well. Well, thanks for watching this part, and see you in the next part.